The race to the bottom has been won with a direct drive extruder, 360-degree part cooling, filament runout detection, and touch probe bed leveling, all for around $200. This is the MVP of 3D printers. Anything cheaper is a toy. Unless unless Creality finally gets their act together and makes a Core XY 3D printer for the same price as an Ender 3, which is totally doable, by the way. You're not going to see this printer becoming usurped as the king of low-cost, high-functionality 3D printing anytime soon. I've designed it so that it can be made with the lowest possible effort and time spent. So let me show you how you can make it too. So to do this build, of course, you're going to need to buy some things, starting with the Ender 3 here. Now, the cheapest place that I found to buy it online is Creality3D.shop. I think this is the official Creality, although there's another website which is called Creality 3D Official or something like that. So China is not immune from their own copycatism, and I think that this is the actual Creality website. So yeah, go there. It's $180 and then shipping. Now, all things told, with taxes and shipping, I ended up spending $210. And yes, I purchased this Ender 3. Creality's not giving these out anymore. This isn't something they want to publicize. It's already the best-selling printer in the whole world, and they want you to buy their newer printers with higher profit margins. I think that there's a new version of the Ender 3 out there even that reviewers are looking at these days. So I'm not really interested in those. The incremental advancements in them don't seem all that useful to me, and so instead I think it's far better to start with the absolute cheapest printer that has a functional motion system, which you can get, and of course that's the Ender 3. That's why it's just such a hugely popular printer in the world. The next thing you're going to need to buy from China is this bundle of stepper motor wires. On one end there's a plug to plug it into the stepper motor itself, and on the other end it's just got loose dangling ends. Now, this is the cheapest wiring that I can find for you guys. I'm not going to provide links. You can find it. Just go to eBay. This is also on AliExpress, I think. It's $3 before shipping here on the listing that I've found, and you're going to need 2 of these if you don't have any other wires. But if you already have some wiring, I think this might be 18 gauge. Yeah, if you already have this, then you don't need to spend the money here. Moving on, you're going to need an optical sensor. Make sure you get one that looks like this. This is very important. This one here is wrong. Do not buy the red one with the plug on the opposite side of the fork optical sensor. This one with the wiring plug on the same side has the little component that you can see my mouse hovering over right there. And that little component cleans up the signal to the control board so you get less false positives. So this is the more advanced board to buy. But a word of warning, make sure that you get the wiring, the 3 wires, correctly wired to the board. If you switch the polarity on any of the wires, it's going to burn up that same little chip and you'll have a bad day. You'll need to get a filament runout switch, and there's many of these. These are the cheapest ones that I've found. I get 2 of them for $1.68, also from AliExpress. You're going to need a single DuPont connector to take a bare wire and put it onto a pin on the control board. If you don't want to buy this, you could solder that wire to the pin if you want to make it a very permanent solution. But for like $1.50, I think it's a good idea to buy some of these DuPont jump wires. Alternately, you can get DuPont crimping kits where you can crimp DuPont connectors onto the ends of bare wires like this right here. So that's going to be more expensive, and it's just easier if you do it this way. And finally, you're going to need 2 10K ohm resistors, 10,000 ohm resistors. I found them here for $1 for like a 20 pack or something like that, but you only need 2 of them. There's only 3 parts that need to be 3D printed. The first of which is the integrated fan duct and sensor mount. Now, this part needs to be printed with ABS filament, and ABS releases nanoparticles as you're printing it. So it's a good idea to not be in the same room with this print, because inhaling those is not great for your health. Also, because it's an ABS print, which is prone to warping up off the bed, you'll need to set your bed temperature to like 100 or even 110 degrees. And that will cause the bed to warp, to bubble either upwards or downwards. So when you level all 4 corners of the bed, make sure you, again, measure to the middle of the bed with the paper underneath the nozzle to see what you need to do as far as micro-step adjusting for the print, which will be happening there in the middle of the bed. In other words, make sure that the first layer is not going down too close to the print surface, because if the nozzle's dragging on the print surface, or even if you're just printing too closely, you can easily damage the knockoff build tack print surface that comes with your Ender 3. You can see here on my print where the outer layers of the brim were actually too close to the bed, and I had quite a struggle getting them removed from the print surface. The next thing you need to print is the direct drive stepper motor mounting bracket. I printed mine out of PETG filament, although you could use the same ABS that you used in the last print. By the way, you can buy small quantities of filament, which are typically meant for 3D printer pens, but I find those mini spools to be just about the right amount for these brackets. So while those two brackets are printing, we're going to tackle the hardest part of the whole build, and that is the wiring loom. All right, this is the easiest way that I've found to splice wires together. I'm not claiming it's the best way, just that it's the easiest way, and I've had zero problems with all of my printers using this method. So you can do it some other way if you feel that that's more appropriate. I just put the shrink tubing on it like so. I put the two wires together, spin them up like you normally would. And this is the key part here, you guys. You have to fold the wire twice. So I put a little crimp in it with my fingernail there, and just kind of roll it up. You see that? Makes a nice little ball. And that ball is what resists the pull if I start to pull it apart and try to, separate the connection. Now I just slide the shrink tubing over the knot there and make sure that it's kind of centered. And what happens is the shrink tubing actually helps to hold that little ball of wire together, and this is quite strong. It won't pull apart. Not to mention the fact that because there's no solder in there, all the wires are pliable still, and the connection's not likely to fatigue until it breaks. Showing how to do the wiring is best illustrated using a couple of diagrams. First one here is this back of the napkin chicken scratch diagram, but you can see the actual photos of the units. So these two things here are the 10,000 ohm resistors. I had you order a few of those. So this one right there that connects the positive line to that signal line, that's called a pull-up resistor. And then the other one is an inline resistor, and you need both of those for the system to work. And like I said, make sure right up here on this switch that you get those wires connected correctly, that red is going to voltage and black is going to your ground. And on the back side of this switch, there's some screen printed letters which will tell you which wires are which. So don't just rely on my diagram for that. Make sure you're looking at the actual switch. Same goes for the control board. You can't see it here in the face, but if you flip the board over on the backside, you'll see that power, ground, and signal are in this orientation. So just double check, you don't want to burn anything up. And the last thing to point out in this diagram is that the signal line coming from the optical switch is going into the out. It's labeled out. It's the far pin there on that 5-pin connector. The second diagram here is more sterile, but also more information rich. And you can see right there in the middle, that 1 meter length of wiring where you got some different odd colors. You get those wires from the second stepper motor wire bundle that I had you buy. The first bundle, of course, will be used to extend the actual stepper motor wiring for the extruder stepper motor. And that is very straightforward and self-explanatory, so I'm not going to cover it here in the video. When you make the loom here, you will be using 3 of these 3-pin connectors, and these come in the bag with the respective switches. So the optical switch that I received had a red, black, and white wire, and the other end got cut off and discarded, whereas the 3-pin connectors for the filament runout switch on mine had a black, red, and green wire, and you can see I used the other end over here. So you'll want to cut these to the lengths that you see on screen, and I do recommend that you make the connections as I've illustrated here because it will result in the least possible number of connections, and you want to limit cuts and connections on wiring looms as they are the points of the loom that are most prone to failure. So this will be the least likely to let you down. The final thing to note in this diagram is the little DuPont extension cable here with the connector attached to it, and I've drawn that in bright purple just so that it's clear that that's a random piece of wiring, which you will have pulled off of one of your bundles here. And of course that needs to be a female DuPont connector there. So once you've got this loom made and you've got the extended wire for the stepper motor, you can feed those through the snakeskin wire holder on the printer and you're ready for the next task. Installing the fan duct sensor mount is a bit of a chore. It requires disassembly of a large portion of the X carriage. You need to remove all the wiring from the hot block and take the whole hot end off of the X carriage itself. Then the hot end heatsink assembly gets slid up inside the bracket. Now I could have made this more easy to assemble, but it would have come at the cost of a trade-off. Instead of the air just blowing through from the front and then out the two sides, air would have also been blowing downwards onto your print, which is a big no-no. So yeah, it's a little hard to put together, but you'll end up with higher quality prints. The next thing to do is to take a 1/16 inch or 1.5 millimeter drill bit and remount the hole. To do this, I just sort of passed it back and forth in there like I was sanding the inside of the hole until the 1.5 millimeter Allen key that comes in the box with the printer can easily slide in and out of that hole. Okay, next we need a 63.5 millimeter length of Bowden tube, otherwise known as PTFE liner. Now, this isn't really a Bowden tube because we kind of have a direct drive or just like an extremely short Bowden tube, like 3 millimeter long Bowden tube if you want to think of it that way. So if you never plan on putting the printer back into the stock Bowden setup, now there are some advantages to Bowden setups, which we'll cover later. So maybe don't cut up the Bowden tube that came with the printer. Maybe you should order this new short length of PTFE liner just so that you have that option of switching back and forth. By the way, it's got a 2 millimeter inner diameter and a 4 millimeter outer diameter. Getting the two 3D printed brackets installed is pretty self-explanatory. The stepper motor bracket uses the axle bolt for the top left Delrin guide wheel, and the fan duct sensor bracket uses the two screws which held the original metal bracket in place. Sliding the PTFE liner into its hole, the rest of the assembly should be pretty obvious. But you should only use 2 of the stock screws mounted diagonally to hold the radial hot end cooling fan in place, because we need the other 2 screws to mount the optical sensor to the side of the bracket. In my experience, having a loose filament runout switch is desirable. It allows you to first thread the switch and then thread the filament into the hot end. Now that the new X carriage is fully assembled, check out the behavior of the optical switch. It easily registers when you use a piece of metal to break the infrared beam in between the little fork there. But using some printed geometry made out of that ABS, which looks translucent, it doesn't actually break the beam. The beam is able to somehow shine through this. Even after I cover the whole part with ink from a Sharpie marker, I still get the same behavior. But this dark gray PLA filament is able to trigger the optical sensor without a problem. So you will need to do the final print out of a similar material. Test it before printing. When printing the Allen key / sensor gate end piece, if you're using 0.25 millimeter layer heights, make sure you stop the print at right around the 45% mark. Now, I'm going to include G-code for all 3 of these prints, which will work perfectly on the stock Ender 3 to my Patreon supporters. This is the only part of the whole build that I'm going to paywall. You'll be able to access the STL files through the link in the description, but I can't post G-code files to just any old site. I guess I could get them on GitHub, but generally speaking, you shouldn't trust G-code files coming from the internet. They could house a virus or something like that. So the Patreon supporters are going to be able to just use my known working sliced files. And yeah, this one slices where 45% is the time where you want to pause it. And I would build in an M600 automatic pause at the correct layer height, except that the stock Ender 3 does not have the Marlin firmware build with the M600 functionality enabled. So it wouldn't work anyway. You're going to have to just keep an eye on this print. It's a short print, like 10 minutes long. So just keep an eye on the print, and when it gets to the 45% mark, pause it and install the Allen key like you're seeing here on the screen. Next, we need to trim this overall sensor length to be a little over 46 millimeters long. I used some snippers on a burly pair of pliers and then a file to sort of flatten the end, but you could also use a Dremel tool with a little grinding disc if you have that at your disposal. Once the sensor pin gate assembly is at the correct length, you'll find that it has a little bit of wiggle, and I could have made the tolerances in the part a bit tighter, but it would have led to challenges during printing. So instead, what you'll need to do is use a soldering iron or a lighter to sort of melt and pinch together the plastic around the 2 ends of the little 3D printed geometry. This should stop the wiggling movement. Let's talk about the firmware real quick, because it's going to appear to just magically function perfectly when in fact it was one of the most challenging aspects of this build. And I started to go back down the rabbit hole into Marlin, which I haven't touched for like 3 years. I think it's been 3 years since I did a Marlin build. And getting my head back into the game, yeah, Marlin is convoluted and it's not easy. So I actually reached out to another 3D printer channel. This is 3D Printscape. He's got 10,000 subscribers. He's very skilled, you guys. I've never talked to him in person. I pretty much just said, hey, can I get you to make a build for this printer? And he agreed. So just massive thank you to him. And he did a great job. So I'm going to put a link to his channel in the description. Please follow that link. I think he might have some specifics about this build, and if not, he's just got some great general information about Marlin if you're curious about that whole process. But for our purposes here, we're just going to take an 8 GB micro SD card. You can use the one that came with the printer. I would save all of the files on that card elsewhere if you're going to use that one, because you need an empty card with nothing else on it except the file, the firmware file from the description. Stick that file onto the micro SD card, stick the SD card into the printer, and it's magically going to update the firmware and everything's going to work. It's just that easy for you guys. And it wasn't always like this. The last time I was dealing with Marlin, you had to compile the code and upload it through the Arduino IDE and all kinds of complicated stuff. So it's gotten a lot easier. In order to calibrate the offset distance between the touch probe tip here and the nozzle, which is going to vary depending on where you cut that Allen key, right? This is going to vary quite a bit between our printers. So what you do is you go here to Configuration, Advanced Settings, scroll down to Probe Offsets, then Z Probe Wizard. Make sure that the probe is seated where it's supposed to be. So fully in the hole there, and then with the light kind of turning on and off when you activate the probe. Hit the button. What's going to happen is it's going to home first. And you don't want to have that probe tip nicking the clip here or anything else. So I like to pull the probe up and sort of twist it to the side like you're seeing there. It's going to home the Z based on this limit switch right here, and then it's going to travel over there. And you need to get it seated and ready to go. There you go. See how I did that? So as soon as it reaches the height there, it's going to dive, and now it's done a probing measurement. It moves the nozzle to the exact location where the probe just happened. And what we're going to do is move it down. And we're pretty much going to move it down to 0. But you've just got a piece of paper under there, and as you're moving it down, you're feeling. There it is. You come back out here and you scroll down to Done, and that's going to save. So our Z probe offset is negative 3.7. Now go Configuration, Store Settings. If you turn your printer off and on again, you should see a negative value for your probe Z offsets. Now there's only one danger condition that you have to keep your eye out for with this probe. It's not going to be tragic, it's just not going to be very good. And that is to have this binder clip right here at the corner while the probe is down and the print head is pretty close to the bed. So you can see the probe is actually touching the bed. It can also be bad if you're in that condition right there. So when you start a print, there's going to be a command. And that command is G29. So what you want to do is get your start script open for your printer, and right after the home all command, which is G28, you want to add a G29. So G28 will home in the lower left corner using the original Z axis end stop switch, and G29 will use the bed probe to run a 9-point algorithm. So to get from this position to the home position, we're going to get a collision between the pin and the clip here. Shouldn't be too tragic. It will just knock the clip off. This is pretty robust, but it's better to avoid collisions if you can. So the trick there is to kind of, violently force the bed out of the way. Typically your stepper motors will be turned off, and so any location that's just not sort of in that little strip will be okay. So I'm ready to start a print, which means that I need to get the probe into position here, ready for bed measuring. And you can see that the nozzle is almost up to temperature.
once it gets to the desired temperature, that being 195 degrees here, it's going to automatically home and then do a G29 bed algorithm. Okay, when it gets to the last probe point, you have to be ready. You're going to pull that probe out of there so that it can print without the probe colliding with the print geometry. The last color I used was black here. I haven't used this white yet. So we're going to start to print white here. Got that clip in the wrong place. Let's put that clip here on the corner. Put this clip out here on the corner as well to give it a lot of extra space. And I like to store my probe right up here at the top with a magnet, but you know, you could maybe make some sort of a clip up there as well. And you can see this is my little bed test, and it is laying down the outer ring here just to make sure that it's at the correct height all the way around the edge. And what happens if we go back here, we can see that the stepper motor is in fact making micro adjustments. I hope you guys can see this on camera. You see how that little tick mark right there just sort of migrates a little bit from side to side. There you go. So basically these are the corrections that it's making as it's printing, and I can feel it with my fingers. So that bed is not perfectly planar, and there's also a bump to it. So it's bumped up here in the middle, and that non-planar bed is being corrected for with Z motion here. Here's a quirk in Marlin that's important to know. If you're going to remeasure the probe offset between where the probe is measuring the bed and the actual nozzle distance, what you need to do is reset defaults. So that's in the configuration, restore defaults. Now, this might happen to you where it tries to print in the air and it's nowhere near the bed. It's because your Z probe offset is a positive number, not a negative number. And most likely this happened because you forgot to save the value into EEPROM after you did the configuration. So on this bed adhesion test, I didn't get the greatest adhesion down here in this corner. You can see it's sort of peeling up from about there to there. Over here it's good. It's good everywhere else, but that's just the sort of outer line here. It's printing in the middle. Let's stop the print because I don't need it to go any further. And we'll peel this center portion off to take a look. So we can see it's mostly adhering, but there's a slight amount of non-adhesion between the lines. So the nozzle could stand to be just ever so slightly closer to the bed. And in order to achieve that, you just go to configuration, probe Z offset, and you increase that distance by making this a larger negative number, and more negative, in other words. 3.82 ought to do it. And of course, you want to configuration, store settings once more. So what's happening here, actually, the reason it's not adhering is because the part cooling fan duct is colliding with this clip right here. And it lifts the nozzle up off the bed. The solution to this problem is pretty easy. Get yourself some of these Swiss clips. These are used for picture frames, and use these at the front of the bed instead of the binder clips. You can see it's just so much more of a minor intervention. And that's the way the adhesion test should look. It's really crisp as far as the corners go, and it's just well adhered down everywhere. Back here you can see I'm still running a binder clip on both of the back corners. It works. I could even cheat it just a little bit more by pulling the binder clip to the very edge of the bed, but it's probably a good idea to get 2 more Swiss clips back there. Now, the last thing I want to test is filament runout. So we're just going to cut this like so. Print paused. Filament change. Feed it back through there. It's beeping at me to let me know that it ran out of filament. Continue. Yeah, that first layer is going down beautifully. So there you have it, a very functional, professional level 3D printer for newbies and print farms.
So now that we've got the printer built, I want to put it into context because there are so many really neat tech innovations for 3D printers. Some of my favorites are anything made by the Duet 3D company, pretty much anything made by Slice Engineering. I like Bontex extruders. There's just some really clever engineers making some really great top shelf devices which make your printer function just that much better. Now, these companies are usually based in Western countries, and as such, they need to pay Western engineers Western salaries, and then they've got to try to make it. Usually, I mean, sometimes they make it in China, but a lot of the times it's made in America, where you got to pay Western workers American wages or European wages to make the things. So they're a lot more expensive than the race to the bottom printer here that we've built. There's a wise adage that the last 10% takes 90% of the time. So, if it takes 90% of the time, time is money. So it also costs 90% of the total cost. So these amazing and definitely undeniably better components made by Western companies cost 90% more, or maybe not that much, but they cost a lot more. And are they needed? Are they really needed? Or is it okay to have just a 90% printer? There are quite a number of 3D print farms that I've seen which use stock Ender 3s to produce parts for sale. So just the stock Ender 3, before we even did the upgrades to it, is already not a toy. And I would classify the stock Ender 3 as more of an 80% printer. We've gotten it up to that 90% level with a pretty minimal amount of effort. And so now it's undeniably not a toy. The features that we've added take it that extra step to really cement its status as a professional printer. Very entry-level professional printer, but still a professional printer. So starting with the filament runout switch, that allows the printer to know when it's run out of filament, to trigger that runout condition and pause the print right there. So now if you're running a print farm, you don't have to worry about whether or not you have enough filament left on the roll. You don't have to guess or weigh the roll or something funky like that. If you've got many rolls of the same color, you just print until the roll runs out, the sensor trips, it signals, and then you change the filament and continue the print right where it left off. So that's just like a no-brainer. Every printer should have that. Without that function, what you end up with is a bunch of sort of tailings, little bits of rolls left over because you're not willing to risk that that's enough on that roll to finish a print. And this is especially important when you're printing like a 10-hour print and you're trying to guess, oh, I think I've got 10 hours worth of filament there, but you don't. And it runs out in like the last half an hour or something like that. And the print is ruined, but it's 95% completed. So now you have to waste all that filament, just throw it in the trash. And you have to wait another 10 hours for your print to actually print successfully with the new roll of filament. So the filament runout switch is absolutely an essential part of a 3D printer in my estimation. But the filament jam detection is not. Very rarely when your printer is up and running correctly will you ever experience a jam. It's just a very rare event. And when you do experience a jam, you'll know it, right? So the filament jam detection, sometimes it saves your bacon, but usually not. The print's usually ruined anyway. So that switch for runout is really what you need, and the jam detection is just kind of a nice to have. It's one of those 99%, one of those extra 10% features that's really hard to implement, and the value that it adds is debatable. So the next professional level feature that we've added to this printer is the physical bed probe, the Allen key bed probe, and touch sensors. Touching the print surface itself are absolutely the best. And there's pretty much two ways that you can achieve this. One way is with a pin or an actual little probe that touches the bed, and the other way is to use the nozzle itself. Typically, you're seeing this these days with a a strain gauge, like a digital scale, so it can measure the pressure when the nozzle hits the bed. Now, it's the keep it simple, stupid rule, right? You want to remove components, unnecessary components. And with a strain gauge attached to the nozzle, you actually don't have a moving component. It's all a solid piece. So it's some really cool technology that's involved in that. But there's a drawback. The fact that you can't measure your bed with a cold nozzle, because there's a possibility that you have some hardened and dried old filament from the last print that's kind of like a little bubble hanging out of the tip of the nozzle. Or even worse, maybe you have a bunch of buildup on the nozzle and you have the same problem. So then you heat the nozzle up, but you have a bunch of buildup on the nozzle. Even with heated up, it's still soft and squishy. So now it's sort of like, where is it triggering the scale, the strain gauge? Where in the squishing all that old filament out of the way is it triggering? So not as accurate as a pin. So yeah, I tend to lean towards physical touch probes for bed leveling, and judging by the success of the BL Touch and all of its clones, I think that technique is kind of, by popular vote anyway, a winner. But that's not to say that the using the nozzle is not valid. And in fact, I think that it's really cool. So in this case, because it is kind of a toss-up, and because I was able to implement touch probing so inexpensively, that's the direction that I went. And I want to make it clear that I didn't come up with this idea at all. In fact, using an Allen key as a bed probe was the precursor to the BL Touch. This was a technique from the DIY space from many years ago, and I've just sort of brought it back for this build. So now let's talk about part cooling. And if it's needed, and it's not always needed, you guys, but if it is needed, then it's really quite nice to have 360-degree part cooling. And the original technique for 360-degree part cooling was literally a circle that tried to blow air from all sides. But the most effective way to actually achieve this is by having a blast of air come from either side of the nozzle. And right there at the sides of the nozzle, what happens is the two blasts meet, and then the wind gets sort of blown out through the sides and actually back towards the nozzle. So you get 360-degree cooling by just having two jets of air from either side. Contrast this with single-sided part cooling, where the nozzle itself can make a shadow on the far side, like a wind shadow. So if you're printing in this direction, none of that wall which you laid down is actually receiving any of the cooling air. So I have no idea why any company is selling a printer without split part cooling on it. It just makes so much more sense, you guys, but it is what it is, and consequently we are forced to upgrade our own printers with split part cooling ducts. Now, of course, there are superior solutions to the part cooling that I've implemented, because that tiny little anemic fan is not really up to the task if you're going to be printing anything faster than, like, I don't know, somewhere between 40 and 70 millimeters per second. So the Berg Air is a really crazy cool upgrade for part cooling. And if you've watched the videos for the Benchy Speedboat Challenge, these guys are just blowing massive amounts of air because they're printing so quickly. They really need to cool that print very quickly. So yeah, of course, there's upgrades available there. But again, these are 90% level solutions that I've created. And if you want to get above that 90%, you're really going to spend a lot of money to get that last 10% performance. And finally, let's talk about the direct drive extruder, because it's pretty much the consensus out there that direct drive is the superior extruder technique. And the reason it's superior is because that short filament path means that the filament itself behaves less like a spring. And when you're printing flexible materials, and really flexible materials like 92A, this kind of a deal, you will find that the material really sort of winds up. It spirals up inside the tube. I mean, there's a tiny little bit of wiggle play for the filament inside the tube, but over a whole length of Bowden tube, there's a spiral in there, and it literally behaves just like a spiral spring. And so when you push on it, the spring sort of compresses, and then it takes a minute at the far end of the nozzle. It takes a minute for that filament to work its way through. So you don't get the instant push that you want, that the printer's trying to tell, you know, the filament squeezing out of it to do. The printer's saying, hey, now push, and there's like a delay. So this leads to artifacts that manifest on the surface of your print that you can see with your eyes. But you also have stringing issues, and that requires more retraction. And yeah, Bowden tubes, generally speaking, are just less responsive, and you want more responsiveness. So direct drive is the superior solution, but it comes at a cost. I'll link to a video and the timestamp down below where I explain the mechanics of what's going on, but let's just shorthand it by saying that having a small hob gear, that's the toothed gear that grabs the filament and pushes it through the nozzle, having a small hob gear causes pulsations in the actual feeding, because the feeding of the filament doesn't happen all that quickly. So these pulsations cause sort of a periodic change of flow. So it changes how much it's pushing through because of where the teeth on the hob gear are. And that manifests as lines in your finished prints. But you wouldn't see these lines on the Bowden tube setup because there's this giant spring attenuating the pulsations, effectively acting like a shock absorber in your car, absorbing the bumps on the ground. So if you want those just glossy, smooth, beautiful walls, you're going to want to stay with the Bowden tube setup at the expense of stringing and sort of like blobbing at corners, that sort of a thing. And one thing that's nice about this build is it's very easy to undo the 4 screws and just relocate the extruder back to the stock location and go back to that Bowden setup if that's what you're looking for, smooth walls. So you can go back and forth, with about maybe 5 minutes of work if you want the attributes from one or the other systems, the direct drive or Bowden system. The only other criticism which I've ever been able to sort of like throw at a direct drive system is the increased mass, and that can manifest in the print as what's called ghosting or ringing, which is another sort of vertical artifact that you see. However, on bedslinger printers, these Mendel printers, you're constrained by the heaviest axis, and in this case, that's the bed. So even with this heavy stepper motor on the X carriage, this whole direct drive system still weighs less than the bed assembly. So yeah, the only reason to switch back to a Bowden setup would be to get those just beautiful smooth walls, but that's going to come at the cost of blobbing and buildup at your corners, reduced retraction performance. You're going to have to increase your retraction to like 4 millimeters maybe. And also you'll have more stringing because of that retraction, because of the delay in the retraction. So yeah, direct drive is the way to go. Now, this is the perfect segue into further upgrades that you can do to the printer, because there is a plethora of stuff. What I've done is to make a printer with only 3 prints that gets you that professional level printer. So the least for the most. So you're doing the least effort, spending the least money to get the most performance, but there's certainly no shortage of other upgrades that you can add to this printer. And starting with the capstan mechanism, that's the actual plastic part that grabs and pushes the filament up against the hob gear. It's been known online from time to time that fails on people. The plastic of that fails. So here's the key. Do not overtension that. In fact, I say don't even add any of the tension in the device. Just leave it, as open as it can be. You'll have enough tension. First of all, overtensioning exacerbates that pulsation problem that I was talking about, which leads to the sort of like lines on your print. But also, overtensioning will be what puts the extra pressure on the plastic capstan mechanism, which will cause it to fail. So there are many solutions here. The first one, I think it's around $8 online. You can find an all metal, just drop-in replacement for the plastic part here. Of course, you could upgrade to the dual drive capstan made by Creality. It's basically got 2 hob gears, so it's feeding that filament from both sides. But the problem with this dual drive is it's still directly connected to the extruder motor, so you're not getting the benefit of any sort of gear ratio, but also the hob gears themselves aren't any larger, and the synchronization of the 2 gears, of the 2 hob gears, have to be synchronized together with a separate set of involute gears. And depending on how closely meshed those gears are, you'll get slop in those gears. And that slop there will exacerbate the witness lines that I've been talking about on your print from the teeth spacing on your hob gear. So the solution to the witness lines is to go with a larger hob gear, and you'll find that in the Bondtech LGX, which is my favorite, but that's a $99 extruder. You can certainly add that pretty easily to this printer. Or if you only want to spend like $50, there's the Orbiter extruder with the slightly larger hob gears. So much better off with the LGX, but there's going to be steps. You want to spend $25, there's an extruder option, but we're just now making this transition in the hobby away from these smaller hob gears into larger ones, and in the future I think there's going to be a lot more options there. So maybe just wait and deal with the witness lines. They're not catastrophic, and that's just the price that you pay for the superior responsive performance of the direct drive extruder. So depending on your goals for this printer, if you're a newbie who just wants to keep upgrading it and making it the best possible printer it can be, you might actually print a bunch of add-ons for it. But if you're running a print farm, you're probably more like me, where you have time that's kind of valuable when it's related to 3D printers, and you just want to get the most for the least effort. And so I think that the upgrades that I've done here are that. You really don't need to add anything above and beyond what I've done. But if I was going to upgrade this printer further, these are the 5 upgrades I would do, and this is the order that I would do them in. Starting with a Raspberry Pi. Now you can go with the Raspberry Pi Zero W, the original, which costs like $10. You can still get that online. You can go with the new version, which is the Pi Zero W2, and that's got more performance. So you could actually put a webcam on there. But the Raspberry Pi gives you the ability to run Octoprint. And Octoprint is a wireless interface for your printer. So you can log into a web page and upload your G-code files from across the room. With that webcam, you can actually see what the printer's doing on your computer, so you can kind of monitor it from a distance. But I find Wi-Fi functionality to be a really nice to have, but not necessary. So that's why I didn't go to the trouble to put a Raspberry Pi on this build for everyone. However, if you are running a print farm and you have many printers to manage, maybe you would find that webcam functionality useful. So I think that is going to be a debatably very useful thing to add to your printer. So that's the number one thing that I would add above and beyond what I've already done. The number two thing that I would add above and beyond what we've already done is my nozzle wiping brush. Now this is a whole separate thing that I've already made a video about. I'll put the link in the description down below. But basically, if you have wet PETG filament, you're going to have severe problems with stringing, and that stringing builds up on the nozzle, which makes a big glob of filament on the nozzle, which is kind of sticky. And as the nozzle's passing over your print, it's likely to catch your print and tear the print off the bed or cause skips in the print, that sort of a thing. So you have one of two solutions here. One, you keep the PETG filament very dry, or you only print with a brand new roll of PETG filament, or you wipe your nozzle. And with the right slicer, that being Super Slicer on GitHub, you have the ability to have that nozzle dart off to the side and wipe on the brush every couple of layers or something like that, just to keep that nozzle clean so that you avoid this problem. But you might find it just easier to dry your filament before you're printing with it. And hey, I have a video about a really inexpensive filament dryer also in the description down below. The number three add-on which I would do is my bestest filament spool hub. And I put that in quote because it's this much better than all the other options. There's a video. You can watch that video and see what I'm talking about. But even though it's ranked number three, it might be the first thing that you guys actually add to your printer above and beyond, because it is really easy to print and bolt on there. It doesn't require any thinking. So it's easy, it's fun, why not? And it does provide some nice functionality. The primary advantage to it is the fact that there are ball bearings that are perfectly centered in that filament spool. So the filament spool unwinds perfectly smoothly. Whereas when you're using the stock setup, there's a chance that the spool sort of like tilts for a second before it slides. So it tilts and it sort of shakes, and that shaking causes the whole printer to sort of vibrate for a minute, which can manifest on the print surface. So if you are after the utmost quality of prints, then this is certainly an attractive upgrade. So number four here would be the solution for eliminating printer vibration that CNC Kitchen came up with. So there's a video of his, I'll link it in the description down below, where he basically puts it on a concrete paver with foam underneath that, and it's just such a rock solid foundation that you don't get any of that wiggling of the printer. So again, it cleans up the witness lines in the surface of your print and just makes your prints look that much cleaner. And the fifth thing that I would do is my combined cooling tower. So there's a video about this one in the description as well. And basically I move the location of the control board to a place where I can use a 120 millimeter fan to cool both the control board as well as the power supply. So we're getting rid of two very loud, small fans that don't move as much air. So we're getting better air supply and quieter printing. So it's kind of an advantageous thing, but it is bit of effort, so check out the video for that one. And of all those 5 upgrades, the most expensive has to be the Raspberry Pi, which is going to cost you $10 to $15. The other ones are all like under $5. So those are the 5 budget upgrades above and beyond what I've already made here. But if you want to throw some money at the printer, the best gains in performance are to be had at the extruder itself. I already mentioned upgrading to a Bondtech LGX or possibly an Orbiter extruder. Well, you're also going to want better flow characteristics at the hot end. So the number one thing that you can do is to change that heat break throat from the PTFE lined one that comes on it to the copperhead throat from Slice Engineering. That is just a fantastic upgrade that's going to cost you a little bit more than $30. So pretty expensive for a tiny little piece of metal, but there's just so much intelligence built into that design, and it really does give you some benefit. For instance, you'll be able to print at a much higher temperature than 265 degrees. You're limited by the Bowden tube. the Bowden tube starts to burn at higher temperatures than 260 degrees, which releases some very, very nasty chemicals. So you absolutely don't want to exceed that temperature at the Bowden tube. And by putting the copperhead heat break there, you're going to be able to up the temperature, which means you can print nylons or polycarbonate or all these high performance plastics. People call this all metal, but that is old nomenclature, shouldn't be used anymore. So the lined heat break versus an unlined heat break is the issue here. And the other option you have for an unlined heat break or an all metal hot end is the Micro Swiss hot end, which is a bolt-on replacement for the hot end that came on the printer. It fits in the same form factor. So it's going to be a new heat sink, a new heat break, and a whole new hot block. Now that heat break is made out of titanium, and it's a separate part that bolts onto the hot block and onto the heat sink in a kind of a tricky little way. It's very, very clever. But the problem that I found with that particular hot end is it tends to jam if you do not completely remove the filament at the end of every print. So while the nozzle is still hot, you have to fully pull the filament all the way out. What tends to happen is the heat creeps up the filament past the titanium heat break. And so the molten filament ends up bonding and cooling against the walls of the heatsink above the titanium heat break. So the next time when you go to heat up your nozzle, the heat can't creep up through the plastic because it's not really there. It's kind of bonded up at the top, and you can never get it warm enough to break it loose from that moment up there in the heatsink. So you end up taking that apart quite a bit if you don't remember to fully pull the filament out after every single print. Other than that, it's a really great solution. And of course, there's lots of knockoffs for maybe like 15, 20 bucks online, but I still think you're going to be much better served to get the copperhead heat break. You're not going to have that jamming issue, and it's just going to be easier to install it. All right, so you want to build it. Where do you get the files? Follow the link in the description. Now, on all of my other builds that I've ever done, this has been a perk for my Patreon supporters. These are the Patreon supporters. And these guys make the channel possible. I'm not even exaggerating in the slightest that I would not be making videos like this one that you're watching. I would not be providing this value to the community or to the hobby if it wasn't for these magnanimous folks who help me to keep making videos. So typically, this is my reward for these guys who help me make videos is having access to the files that I've created. But in this case, I feel that there's just so much valuable for newbies, and I want to encourage people to come into the hobby. And there's so much value for entrepreneurs who might want to start a print farm to be able to use this printer. So I'm just releasing these like open source. So they're going to be posted on Thangs, and you'll easily be able to download them there and follow the video here and build up a printer just like what you're seeing. Now there's one exception to this, and that is the actual printable G-code files. So I have generated some really great printable files for these components that work on the Ender 3. So all you need to do is take my G-code, put it on the SD card, stick it in the printer, press print, and you're highly likely to get a successful print because it's all of the settings that I used for those prints. Now, there is some debate about how safe it is to be downloading G-code files. So this is not a general practice, and it's also not something that I can just post on Thangs as far as I'm aware, because it's an executable file that could contain a virus. So if you want the G-code files, sign up on my Patreon page and ask me for those, and I don't know, roll the dice that I'm not going to be giving you guys a virus for your computer. So there's that. But yeah. All right. Well, hey, big thank you to my Patreon supporters, those guys I just showed. And also, these are my producers and executive producers. They really help to make the magic happen around here. That's it for this video. Thanks for watching. Have a great day. See you soon. Bye.
Well, this is interesting. The rotary encoder click function seems to be malfunctioning. I wonder how many people that happens to.